The universe runs on its own hidden power source. We are about to enter the engine room of existence itself, a place where reality is not just unfolding, but actively generating the energy for its own expansion. This is not a metaphor. It is the cutting edge of cosmology, a field discovering that the cosmos is a self-sustaining entity. For centuries, we searched for an external creator or a prime mover, but the truth is far more astonishing. The ultimate power plant is woven into the fabric of empty space. By the end of this journey, you will see the cosmos not as a static stage, but as a dynamic, self-operating machine. We will uncover how nothingness can spawn particles, and why the vacuum of space pushes galaxies apart. What single idea about the universe most challenges your sense of reality? Long ago, inventors dreamed of a perpetual motion machine, a device that could run forever without any outside help. On a cosmic scale, such a machine actually exists. It is not magic, but physics. The universe operates on a principle of cosmic self-sustainability. It contains within its own fabric all the necessary components to generate, maintain, and even accelerate its own existence. This idea transforms our understanding of the Big Bang. It was not merely a one-time event, a single explosion that flung everything outward. It was the ignition of a continuous, self-perpetuating process. At the heart of this process is what we once called nothing. The vacuum of space, far from being a true void, is now understood by theoretical physicists as a seething, bubbling plasma. It is a quantum field teeming with potential energy, where virtual particles flicker in and out of existence in a relentless dance. This foundational view redefines the cosmos from a static expanse to a dynamic, self-operating system. And at the core of this system lies its primary fuel, a mysterious pressure inherent to the vacuum of space itself. This quantum noise is the universe's original power source. Think of the vacuum of space not as an empty stage, but as a bubbling cauldron of pure potential. Here, at the smallest scales imaginable, reality itself is in a state of constant, frantic activity. Pairs of particles and their antimatter twins spontaneously flicker into existence, borrowing energy from the void for an impossibly brief moment before colliding and vanishing back into nothingness. This endless dance of creation and annihilation is not a flaw in the system. It is the system's fundamental hum, the primordial fuel for the cosmic engine. This phenomenon is tied to a profound concept called zero-point energy. It means that even if you could cool a region of space down to absolute zero, the coldest temperature possible, it would still possess a residual, irreducible energy. The vacuum is never truly empty or still. It is alive with this foundational activity. How can something come from nothing? This is how. These quantum fluctuations are the answer. They are not just theoretical curiosities scribbled on a blackboard. Under the right conditions, this background static can be harnessed and amplified on a colossal scale. During the first fleeting moments of the universe, a period known as cosmic inflation, space expanded at a rate far beyond the speed of light. This violent stretching acted like a cosmic amplifier, taking those tiny, random quantum ripples and magnifying them, locking them into the fabric of space-time. These amplified ripples became the seeds for everything we see today. Every galaxy, every star, every planet, and even us, originated from those microscopic knots in the quantum foam. The universe did not need an external spark. It used its own inherent quantum properties to generate substance from the void. This is a truly internal power source, the first and most fundamental transformation in the engine room of existence. This initial quantum noise was then subjected to the most violent event in cosmic history. The universe slammed its foot on the accelerator during a period known as the inflationary epoch. In less than a trillionth of a second, the fabric of reality stretched at a rate that defies all intuition. expanding faster than the speed of light itself. This was not an explosion into a pre-existing void. It was space-time itself being stretched and inflated at an incomprehensible speed. The engine behind this cosmic throttle was not some external force, but a state of the universe's own fabric, a hypothetical field that physicists call the inflaton field. Think of this field as a latent energy bank, a tremendous store of potential power woven into the vacuum. This internal energy reserve was the fuel that drove the explosive growth, stretching the microscopic quantum ripples into macroscopic wrinkles. This single act of cosmic inflation did two critical things. It took the tiny, random fluctuations from the quantum foam and magnified them into the gravitational seeds for all future structure. It also ironed out the cosmos, smoothing and flattening the entire universe into the remarkably uniform state we observe across the sky. The entire large-scale structure of our reality, from the vast cosmic web of galaxies to the faint afterglow of the Big Bang we call the cosmic microwave background, was set in those first fleeting moments. This was the universe using its own internal power reserves to dictate its ultimate shape and destiny. With this explosive growth complete, the cosmos settled into a new, cooler phase, its internal engine ready for the next stage of power generation. With the violent expansion complete, the cosmos entered a new phase of unimaginable heat and density. For the first few minutes, the entire universe was a searing nuclear furnace, a plasma so hot and dense that no stable atoms could exist. Within this primordial fireball, the universe began its most fundamental act of construction. It started forging the very building blocks of matter in a process we call Bang Nucleosynthesis. This was not a factory with external inputs. It was a self-contained, self-regulating nuclear reactor, running entirely on the universe's own internal conditions. Protons and neutrons, the fundamental constituents of atomic nuclei, were bouncing around in a frantic, high-energy soup. As the cosmos expanded and cooled, these particles began to stick together. The first and most critical fusion created deuterium, a heavy form of hydrogen. Once deuterium formed, it acted as a stepping stone. It rapidly collided with other particles, building up the nucleus of the next element, helium. This entire chain reaction was a delicate, self-balancing act. The rate of fusion was perfectly governed by the universe's internal temperature, its density, and the strength of the fundamental nuclear forces themselves. If the density had been just a little higher, nearly all the hydrogen would have fused into helium. If it had been slightly lower, hardly any elements would have formed at all. The fact that it produced the precise amounts we observe is one of the strongest pieces of evidence for the Big Bang model. In just those first 3 minutes, the cosmos manufactured almost all the helium and deuterium that would ever exist, plus trace amounts of lithium. Then, as the universe continued to cool, the nuclear fires subsided. The process simply stopped, frozen in time by the expanding, cooling cosmos. This left a universe composed of about 75% hydrogen and 25% helium, a pristine fuel mixture that would drift for millions of years in the dark. In this act of cosmic alchemy, the universe demonstrated its self-sufficiency once again. It used its own initial energy and internal physical laws to create the raw materials for everything to come. These first, light elements were the primordial ingredients, the universal feedstock, and they were about to be delivered to the construction sites that would shape them into worlds. The first stars did not flicker on one by one. They ignited in a sudden, cosmic dawn, ending the universe's long, dark childhood. For millions of years, those vast clouds of pristine hydrogen and helium simply drifted, a cold and silent fog. But those clouds were not empty. They were seeded with the faint gravitational imprints left over from cosmic inflation. These tiny pockets of slightly denser space acted as anchors. Gravity, the patient architect of the cosmos, began its work there. It is the weakest of the fundamental forces, but it is relentless and cumulative. Over eons, it pulled atom toward atom, amplifying those initial wrinkles into knots of matter. A diffuse cloud light years across would slowly begin to contract, spinning faster and faster as it shrank, its core growing hotter and denser under the mounting pressure. This process of gravitational collapse is the universe's primary method of construction. It is a perfect, self-contained power conversion. The gravitational potential energy of a widely dispersed cloud is transformed directly into the intense thermal energy of a stellar core. When the core temperature reaches a staggering 10 million degrees, a nuclear furnace roars to life. Hydrogen nuclei slam together, fusing into helium and releasing a torrent of energy in the process. A star is born. This is not an external fire being lit. It is the universe concentrating its own raw materials and using its own internal force, gravity, to trigger a self-sustaining reaction. The star becomes a balanced system, where the outward pressure from fusion fights a constant battle against the inward crush of gravity. This equilibrium allows a star to shine steadily for millions or even billions of years, a beacon forged entirely from within. But the star's work is not done when it finishes burning hydrogen. For the most massive stars, their lives are a frantic, multi-stage forging process. As hydrogen runs low, the core contracts further, heating up until it can begin fusing helium into carbon, then carbon into oxygen, and so on, building heavier and heavier elements layer by layer like a cosmic onion. This stellar alchemy creates the elements essential for planets and life itself, the carbon in our bones, the oxygen we breathe. The star's final act is its most spectacular. When it can fuse no further, gravity wins its long war. The core collapses catastrophically, and in a titanic supernova explosion, the star blasts these newly forged elements back into the void. This is the ultimate act of cosmic recycling. The death of one star seeds interstellar space with the enriched material for thousands of future stars, planets, and perhaps even new life. The energy released in these stellar processes is almost beyond comprehension, yet it all originates from the simple, patient pull of gravity on the universe's own primordial gas. This stellar engine is a closed-loop system, a perfect example of internal power generation. But as powerful as these stellar furnaces are, an even more mysterious and dominant force was waiting in the dark, one that would ultimately dictate the fate of everything. While stars forged the elements of life, a far more dominant and mysterious presence was silently shaping the entire cosmic landscape. This invisible substance, known as dark matter, forms the true skeleton of the cosmos. It does not emit, absorb, or reflect any light, making it completely undetectable to our telescopes, yet its gravitational influence is undeniable and overwhelming. We can see its effects in the way galaxies spin. Stars on the outer edges of a spiral galaxy orbit at nearly the same speed as those closer to the center. This defies all expectations. According to the laws of gravity, these distant stars should be flung out into the void, like water flying off a spinning wheel. The only explanation is that the entire galaxy is embedded within a massive, invisible sphere of matter. A halo of dark matter whose gravity alone holds the speeding stars in their tracks. We also witness its presence through a phenomenon called gravitational lensing. The immense mass of a galaxy cluster, composed mostly of this dark matter, warps the fabric of space-time around it. When light from a more distant object passes through this warped region, its path is bent, much like light passing through a lens. This creates distorted, magnified, or multiple images of the background galaxy, revealing the hidden mass that is doing the bending. Dark matter provides the gravitational potential wells, the deep pits in the fabric of space, into which ordinary matter falls. Without this invisible scaffolding, the universe would lack the necessary gravitational glue to pull itself together into the vast web of galaxies and clusters we observe. Its nature remains one of the most profound puzzles in all of physics. Is it a sea of exotic, undiscovered particles? Is it a relic from the first moments of the Big Bang? We do not yet know, but its role is absolutely clear. Dark matter is an integral, internal component of the universe's machinery, the unseen framework upon which all visible reality is built. And as this invisible hand sculpts the cosmos, another, even more mysterious force is actively working to tear it all apart. This accelerating expansion is the universe's most startling act of self-propulsion. Just as we mapped the cosmos, we discovered it was running away from us, faster and faster with each passing moment. The force responsible for this great cosmic acceleration is dark energy, a repulsive pressure woven into the very vacuum of space. It acts as a kind of anti-gravity, pushing the fabric of reality apart instead of pulling it together. The leading explanation for this mysterious force is something called the cosmological constant. Think of it as the baseline energy price for owning a piece of empty space. According to quantum theory, even the purest vacuum is not truly empty. It is a simmering sea of virtual particles. This underlying activity gives every cubic centimeter of nothingness a tiny, intrinsic energy. On human scales, this energy is negligible, completely undetectable. But when you add up the effect across the entire vastness of the cosmos, this energy inherent to emptiness becomes the single most dominant force in the universe. It is a profound and deeply counterintuitive idea. The universe is not just expanding into a void. It is being driven apart from within by the energetic properties of that void itself. The engine room of existence is powered, in its most dominant form, by nothingness. This dark energy now makes up about 70% of the entire cosmic energy budget, completely overwhelming the combined influence of all matter, both dark and visible. Its presence dictates the ultimate fate of everything. In a universe governed by this relentless acceleration, the cosmic horizon will eventually shrink. Galaxy clusters will be pulled so far apart that their light can no longer reach us, leaving future astronomers in a lonely, isolated island of stars, wondering if anything else ever existed. All of this unfolds according to the universe's own internal programming, a set of interconnected systems working in a delicate and dynamic balance. This vast cosmic architecture reveals a universe that is stunningly organized. Zoom out far enough, and the scattered galaxies resolve into a single, magnificent structure, a great cosmic web. This is the largest pattern in existence, a sprawling network of galaxies and dark matter tracing delicate filaments across billions of light years. These filaments connect at dense nodes, where thousands of galaxies swarm in massive clusters, and they surround vast, empty voids of breathtaking emptiness. This is not a random arrangement. It is the ultimate expression of a self-organizing universe, a pattern that grew directly from the microscopic quantum ripples amplified during the inflationary epoch. For billions of years, gravity acted as the master sculptor, patiently pulling those initial wrinkles in spacetime into this intricate, web-like design. Think of the cosmic web as the universe's circulatory system. Along the dark matter filaments, rivers of primordial hydrogen and helium gas flow, channeled by gravity toward the dense clusters. This continuous flow of cosmic fuel is what allows galaxies to form, grow, and sometimes collide in spectacular mergers, sparking new waves of star formation. The entire structure is dynamic and alive with motion, a slow-motion dance choreographed entirely by the universe's internal forces. This complex self-organization, emerging from simple initial conditions and governed only by gravity and dark energy, rivals the intricate patterns found in biology. It shows a cosmos capable of building its own large-scale anatomy from the inside out. And just as the web connects the largest structures, The engine room also operates on the smallest imaginable scale, where another fundamental process gives substance to this entire cosmic tapestry. This cosmic web, vast as it is, may be held together by threads of instantaneous connection. At the heart of this profound interconnectivity lies a phenomenon so strange it baffled even Albert Einstein, who famously called it spooky action at a distance. We now know it as quantum entanglement. Imagine two particles born from the same event, like twins sharing a single existence. They become linked or entangled. From that moment on, no matter how far apart they travel across the universe, they remain a single, unified quantum system. Measuring one particle and finding its spin is up will instantaneously force its distant partner into the opposite, downspin state. This connection defies the cosmic speed limit, the speed of light. Information seems to leap across any distance in zero time. It is as if the universe has its own built-in nervous system, a hidden network allowing its most basic components to remain in constant, immediate dialogue. This deeply challenges our classical view of a universe built from separate, isolated objects. Entanglement suggests that at a fundamental level, separation is an illusion. The cosmos is not a collection of independent parts, but a single, holistic entity. While its direct role in powering galaxies or driving expansion remains speculative, this quantum weirdness is crucial for the universe's internal consistency. It may be the mechanism that ensures the laws of physics are the same in a distant galaxy as they are here on Earth, synchronizing the cosmic engine room. This instantaneous linking hints at a reality where the true currency is not just energy, but information itself. The universe runs on a code more fundamental than matter or energy, a code written in information. This is the startling conclusion of a growing number of physicists who see the cosmos not just as a place, but as a process, a vast, self-executing computation. From the simplest collision of two particles to the majestic dance of merging galaxies, every event can be viewed as an operation, a step in a calculation where the universe updates its own state. The laws of physics themselves are the unbreakable software, the cosmic operating system that dictates how every single bit of information is processed. This perspective, often called digital physics or the it-from-bit concept, proposes that information is the true currency of reality. What we perceive as a rock, a star, or a thought is simply the physical expression of underlying information being manipulated. This idea reaches its most radical form with the holographic principle, which suggests a reality so interconnected it defies common sense. It proposes that all the information describing everything within a three-dimensional volume of space, every particle and every force, is actually encoded on a two-dimensional surface that surrounds it, like a cosmic fingerprint. Think of watching a three-dimensional movie on a flat, two-dimensional screen. The image has depth and detail, but all that information is stored on the flat surface of the film. The holographic principle argues our experience of a three-dimensional universe might be a similar projection from a distant, two-dimensional boundary. If this is true, then the engine room of existence is not just generating power. It is processing an almost unimaginable amount of data. The vacuum energy, the quantum fluctuations, the force of dark energy, all of it could be manifestations of this relentless cosmic computation. The universe powers itself by constantly transforming information, with energy and matter acting as the medium for this transformation. This informational lens gives us a powerful new way to understand the emergence of complexity. How can a cosmos governed by a relatively small set of simple, elegant rules produce the intricate beauty of a galaxy or the profound complexity of life? The answer lies in the power of computation. Simple rules, when iterated over and over again, can generate astonishingly complex and unpredictable patterns. a phenomenon we see in everything from swirling hurricanes to the branching patterns of a tree. The universe has been running its program for nearly 14 billion years, performing countless trillions of operations, and from that relentless processing, the rich tapestry of reality has emerged. This computational view frames the cosmos as the ultimate self-sustaining system, one that contains its own instructions, its own processing power, and its own memory. And at the very heart of this cosmic code lie a few, seemingly arbitrary numbers that make the entire computation possible. These seemingly arbitrary numbers are the source code of reality itself. The strength of gravity, the mass of an electron, the force that binds atomic nuclei, these are not variable settings. They are the universe's fixed, fundamental constants, and their values are precise to an almost terrifying degree. If the force of gravity were even slightly stronger, every star would burn its fuel at a ferocious rate, causing stellar lifetimes to be brutally short, snuffing out any chance for life to evolve on orbiting planets. If it were just a fraction weaker, matter would never have collapsed into the first stars at all, leaving the cosmos a forever dark and formless cloud of hydrogen. The same razor's edge precision applies to the nuclear forces. The strong force that glues protons and neutrons together is perfectly balanced. Make it a tiny bit stronger, and the universe would have fused all its hydrogen into helium in the Big Bang's first moments, leaving no fuel for future stars. Make it slightly weaker, and no complex atomic nuclei could ever form, meaning no carbon, no oxygen, and no chemistry beyond the simplest elements. Even the mass of the electron is a critical dial on the cosmic control panel. If it were different, the very architecture of atoms would become unstable, and molecules could never link together. This is not a matter of slight adjustments. It is a symphony of constants where each note must be hit with perfect accuracy for the music of complexity to ever play. This breathtaking fine-tuning presents a profound question. Why is the cosmos so exquisitely calibrated for our existence? One response is the anthropic principle, a simple but powerful logical observation. We can only find ourselves living in a universe capable of supporting conscious, observing life. If any one of these constants were off by even a minuscule amount, we would not be here to wonder about them. In this view, the universe is not fine-tuned for life. Life is simply a product of the one particular set of constants that actually exists. Yet the sheer improbability of this specific combination has led physicists to propose a staggering alternative, the multiverse. Imagine our universe is just one bubble in an infinite, frothing sea of other universes, each with its own random set of physical laws and constants. In the vast majority of these cosmic bubbles, the numbers are wrong. They are stillborn universes that collapse instantly, or form no structures, or are just empty, featureless voids. But in an unimaginably rare few, like ours, the numbers just happen to line up perfectly, allowing for galaxies, stars, planets, and life to emerge. We find ourselves in one of these lucky universes not by design, but by sheer chance across an infinite landscape of possibilities. This fine-tuning is what gives the cosmic engine its remarkable stability. It is the reason stars can burn for billions of years, providing a steady energy source for planetary systems. It is the reason atoms are stable enough to form the complex molecules that underlie biology. The universe's internal settings are not just random. They are the very reason its long-term, self-sustaining operation is possible at all. This precise calibration, whether by chance or some deeper principle, is the final, silent guardian of the engine room, ensuring the machinery runs smoothly for eons. This relentless drive toward disorder is the universe's most fundamental engine. The laws of thermodynamics, born in the steam age, govern the ultimate fate of the cosmos itself. The second law is king here, stating a simple, inexorable truth. In any isolated system, a quantity called entropy, a measure of disorder, must always increase. The entire universe is that ultimate isolated system, a closed box with nowhere for its energy to escape. After the Big Bang, the cosmos began in a state of astonishingly low entropy, an incredibly ordered and uniform state, like a perfectly stacked deck of cards. From that moment, the only direction it could travel was toward greater and greater disorder. This thermodynamic imperative is not a suggestion. It is the cosmic clock that only ticks forward. It is the reason time has a definitive arrow, moving from a structured past toward a dissipated future. Every single process you witness is powered by this flow. A star shines because it is a massive reservoir of ordered hydrogen, relentlessly transforming into a more disordered state of helium and radiation. A plant grows by capturing the ordered light from the sun and converting it into the complex, yet less ordered, structures of its own body. Even the thoughts in your mind are powered by chemical reactions that increase the overall entropy of your surroundings. This flow from hot to cold, from concentrated to diffuse, from ordered to disordered, is the power stroke of the entire cosmic machine. It gives the universe's self-powered evolution its irreversible direction and its grand, tragic narrative. And in this story of rising chaos, black holes play a paradoxical role. They are the ultimate sinks of entropy, cosmic whirlpools that swallow matter and light into a state of maximum disorder. Yet, they may also hold the key to understanding the final state of the entire universe. Black holes are not the end of things, but a new beginning. These gravitational monsters are among the most powerful engines in the entire cosmos. Picture a star or a vast cloud of gas, straying too close to a black hole's immense gravity. It does not simply fall straight in. Instead, it is caught in a furious, whirling dance, spiraling inward at nearly the speed of light. This orbiting material forms a superheated disk of plasma, an accretion disk, where friction and immense gravitational forces heat the matter to temperatures of millions of degrees. It glows with the energy of a billion stars, pouring out torrents of X-rays and radiation. This is how a black hole powers a quasar, an object so luminous it can outshine an entire galaxy from a distance of billions of light years. The energy for this incredible light show does not come from within the black hole itself, but from the colossal gravitational energy of the infalling matter, a power source generated purely by the warped geometry of spacetime. But the engine does not stop at radiation. Along the black hole's poles, magnetic fields can funnel some of this superheated plasma into narrow, unimaginably powerful jets. These beams of charged particles blast across interstellar space at nearly the speed of light, carving through galaxies and influencing the formation of new stars. In this way, a black hole is not just a consumer. It is a regulator, its violent activity able to heat surrounding gas and prevent it from collapsing into new stars, effectively putting a brake on a galaxy's growth. This is gravity operating at its most extreme, converting matter into pure energy on an industrial scale. Yet, even these titans are subject to the strange rules of the quantum world. Through a process known as Hawking radiation, black holes are not entirely black. At the very edge of the event horizon, the point of no return, the intense gravitational field can spontaneously create a pair of virtual particles. If one particle falls in while its partner escapes, the black hole effectively loses a tiny amount of mass. Over timescales longer than the current age of the universe, this slow, quantum mechanical evaporation means that even the largest black holes can eventually fade away, returning their energy and information back to the cosmos. This reveals black holes as transformative components in the cosmic cycle, places where matter is not destroyed but utterly transmuted, and where gravity and quantum mechanics meet in a final, violent embrace. They are the universe's ultimate recyclers, taking the raw material of stars and galaxies and forging it into new forms of pure, radiant power. Magnetism is the universe's invisible sculptor. This force, born from the motion of charged particles, weaves through the cosmos from the heart of planets to the emptiness between galaxies, guiding and focusing the raw energy of existence. It begins with a simple, powerful process called the dynamo effect. Deep inside a star or a planet like Earth, vast oceans of molten, electrically conductive metal are in constant, churning motion. This rotation and convection, driven by internal heat, acts like a natural generator. It transforms the kinetic energy of spinning fluid into a coherent, planet-spanning magnetic field. This self-generating process is a perfect example of the universe's internal engineering, creating a protective shield and an invisible guidance system from its own internal motions. Without this magnetic envelope, the solar wind would have stripped away Earth's atmosphere long ago, leaving a barren rock. But the role of magnetism extends far beyond planetary protection. In the dark, cold nurseries where stars are born, magnetic fields are the hidden architects. As a massive cloud of gas begins its gravitational collapse, these faint, pervasive fields channel the flow. They guide the infalling material, helping to spin up the protostar and even focusing powerful jets of matter that shoot out from its poles, clearing away excess gas and determining the final mass of the newborn star. On a far grander scale, we see this same principle of magnetic focusing at work around supermassive black holes. The incredible energy of the accretion disk is not blasted out in all directions. Immense magnetic fields, twisted by the black hole's ferocious spin, act like the barrel of a cosmic rifle. They collimate superheated plasma into narrow, focused jets that scream across space for tens of thousands of light years, injecting energy into the intergalactic medium and influencing the evolution of entire galaxy clusters. This cosmic magnetism is not an external force applied to the universe. It is an emergent property, a direct result of the motion of conductive plasmas that fill space. It represents a fundamental layer of the universe's internal wiring, a method for transporting and concentrating energy across incomprehensible distances. And all of this magnetic force, every stellar dynamo and galactic jet, propagates its influence through a silent, all-pervading medium. This dynamic fabric of spacetime is the ultimate stage manager of the cosmos. It is not a passive backdrop, but a living, breathing entity that bends, stretches, and shudders in response to the universe's contents. Einstein's great revelation was that mass and energy do not simply sit in space and time. They tell spacetime how to curve, and in turn, that curved geometry tells matter and energy how to move. This is the core of general relativity, a set of beautiful, intricate equations that describe this cosmic conversation. The path of a planet orbiting a star is not the result of a mysterious force pulling on it. It is simply the planet following the straightest possible path through a valley in spacetime carved by the star's mass. The fabric itself is the medium for all action, the canvas on which every event is painted and the conduit through which all information must flow. We have felt this fabric move. When two black holes, each with the mass of dozens of suns, spiral into each other in a final, violent merger, they do not send out a silent ripple. They slam into the fabric of spacetime itself, sending out waves of gravitational energy that travel at the speed of light. These gravitational waves are not waves in space. They are waves of space, literal stretches and squeezes of the distance between objects. By the time these faint tremors travel a billion light years to reach our detectors, they are incredibly subtle, changing the length of a 4-kilometer laser beam by less than the width of a single proton. Yet we can measure them. This direct detection confirmed that spacetime is a dynamic entity, capable of carrying energy and information across the cosmos. Every massive object in motion creates these ripples, from orbiting neutron stars to the Big Bang itself, weaving a faint, perpetual hum into the background of the universe. The properties of this fabric, its ability to curve and ripple, are not just interesting features. They are the essential mechanics that allow the universe to power its own evolution. Without this malleability, gravity would not work, stars would not form, and the cosmic web could never have taken shape. The geometry dictated by Einstein's field equations is the invisible hand that guides every galaxy, every photon, and every atom. But for all its grandeur, this cosmic fabric has a mysterious, incomplete relationship with the quantum world, a connection that points to a deeper layer of reality we are only beginning to grasp. This final frontier of physics confronts a deep and fundamental schism in our understanding of reality. We have two magnificent and incredibly successful theories that describe how the universe works, yet they speak completely different languages and refuse to be merged. On cosmic scales, Einstein's general relativity paints a masterpiece of smooth, curving spacetime, a continuous fabric where gravity is simply the geometry of that fabric. But in the subatomic realm, quantum mechanics reveals a frantic, probabilistic world of discrete particles and fuzzy uncertainties. Both theories cannot be the complete picture, because there are places where both must apply simultaneously, and in those places, our physics breaks down completely. The core of a black hole is one such place, a point of infinite density where the smooth fabric of spacetime is crushed into a singularity, a place where the laws of physics as we know them simply cease to exist. The very first moment of the Big Bang is another, when the entire universe was smaller than a single atom, a domain ruled entirely by quantum law. To understand the ignition of the cosmic engine, we must have a theory that can describe these extremes. This is the quantum gravity conundrum, the single greatest unsolved problem in theoretical physics. The quest is to find a single, unified framework that can reconcile the vast, geometric world of relativity with the tiny, chaotic world of the quantum. How can the continuous fabric of spacetime emerge from something discrete? The leading candidates offer wildly different answers. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. In this view, every particle is a different note on a vibrating string, and the force of gravity is carried by a specific string, the graviton. To make the mathematics of these vibrations consistent, the theory requires more than the three spatial dimensions we experience, suggesting extra, hidden dimensions curled up into shapes too small for us to perceive. It is an elegant idea that promises to weave all forces and particles into a single tapestry of vibrating threads. Another profound approach, loop quantum gravity, takes a different path. It suggests that spacetime itself is not smooth and continuous, but is woven from a fabric of finite, discrete loops. Picture the fabric of reality as a spider's web of these individual, quantized threads of space. The area and volume of any region come in tiny, indivisible units, a pixelation of reality at the smallest possible scale, the Planck length. This would mean there is no such thing as a true singularity, no point of infinite density, because you simply cannot pack matter into a volume smaller than a single pixel of space. Both theories are monumental intellectual achievements, yet they remain unproven, waiting for a crucial experimental prediction that could confirm or refute them. A successful theory of quantum gravity would be the ultimate blueprint for the engine room of existence. It would tell us what spacetime actually is at its most fundamental level, revealing the mechanics that allow the universe to generate and regulate its own power from within. While this final theory remains elusive, the universe's self-regulating nature is on brilliant display all around us, in the very stability that allows us to ponder these deep mysteries. This self-regulation is the universe's most elegant feature, a system of checks and balances written into the cosmic code. Think of it as a cosmic thermostat, constantly monitoring and adjusting its own growth to prevent runaway consumption. When one process becomes too dominant, another automatically activates to restore balance, ensuring the long-term stability of the entire system. A perfect example of this is supernova feedback. When a massive star reaches the end of its life and explodes, it does more than just forge new elements. The titanic blast wave slams into the surrounding clouds of gas and dust from which it was born. This injects a colossal amount of turbulent energy, violently churning the nursery and effectively turning off the star formation process for millions of years. The explosion heats the gas and flings it outward, preventing it from collapsing under its own gravity to form new stars. Yet, in a beautiful paradox, that same shockwave can also trigger star birth. When the expanding shell of debris from the supernova plows into a colder, quieter gas cloud nearby, it can compress the material just enough to ignite a new round of gravitational collapse. This creates a self-regulating cycle where a star's death can sow the seeds for its successors, pacing the galaxy's evolution and preventing it from burning through its fuel supply in a single, brief frenzy. An even more powerful regulatory mechanism operates at the very heart of galaxies. Supermassive black holes lurking in galactic centers can transform into active galactic nuclei, some of the most energetic objects in existence. As these black holes voraciously consume surrounding matter, they do not do so quietly. The incredible energy released does not just create brilliant light. It also drives colossal winds of superheated gas and blasts out intense radiation, pouring energy back into the galaxy. These outflows act like a global heating system, warming the vast reservoirs of galactic gas. When gas is hot, it is energetic and diffuse, unable to cool down and collapse to form new stars. This black hole feedback effectively puts a ceiling on a galaxy's growth, preventing it from becoming too large too quickly. Without this cosmic governor, a galaxy would rapidly convert all its gas into a single, overwhelming burst of stars, leaving behind a stagnant, aging system with no future potential. Instead, this push and pull between gravity's pull and the black hole's push creates a dynamic equilibrium. It allows for a long, extended, and diverse history of stellar evolution, providing the steady, stable environments necessary for planetary systems to form and, just maybe, for life to eventually emerge. These feedback loops are the signature of a mature and sophisticated system. They show a universe that is not just a collection of parts, but an integrated whole, capable of managing its own resources and guiding its own destiny from within. This internal regulation prepared the cosmos for one of its most profound transformations. A few 100 million years after the Big Bang, the universe was a very different place. It was dark, filled with a thick fog of neutral hydrogen gas that absorbed light, trapping the cosmos in a featureless gloom. Then, a new kind of dawn began. The first stars and galaxies ignited, and they were not like the gentle suns we know today. Many were colossal, ferociously hot behemoths, and they flooded the infant universe with a torrent of intense ultraviolet radiation. This radiation was so energetic that it began to blast through the primordial fog. It slammed into the neutral hydrogen atoms that filled all of space, ripping their electrons away in a process we call reionization. This was not a local event. It was a universe-wide phase transition, a fundamental change in the very state of cosmic matter, powered entirely by the universe's own first generation of luminous objects. Think of it as the cosmos lifting its own veil, using the energy from its newborn stars to clear away the obscuring mist. This process took hundreds of millions of years, a slow but relentless wave of ionization sweeping across the entirety of space. As it progressed, the intergalactic medium was permanently altered, transformed from a sea of neutral atoms into a plasma of free electrons and protons. This monumental shift made the universe transparent to the ultraviolet and visible light that would follow, allowing the light from all future galaxies to travel freely across billions of light years. Without this self-engineered clearing, we would see almost nothing when we peer into our telescopes. The cosmic landscape would remain hidden behind an impenetrable wall of hydrogen. Reionization also left a permanent stamp on the cosmos. The intense radiation heated the remaining gas, making it harder for small galaxies to form by preventing gas from cooling and collapsing. This effectively put a lower limit on the size of galaxies that could thrive, shaping the population of galaxies we observe today. In this grand act of cosmic self-illumination, the universe demonstrated its ability to not just build structures, but to fundamentally alter its own global environment. It used the collective power of its internal components to switch on the lights for good, setting the stage for the rich and transparent universe we now call home. This ancient blue light is the oldest photograph ever taken. Stretching across the entire sky, it is a ghostly afterglow from a time when the universe was a mere infant, just 380,000 years old. We call this the cosmic microwave background, and it is the single most important piece of evidence we have for the Big Bang. When the universe cooled enough for the first stable atoms to form, light, which had been trapped in a dense plasma, was suddenly set free. That initial flash of liberation has been traveling ever since, stretched by the expansion of the universe into the faint microwave whisper we detect today. But this background is not perfectly smooth. When we look with exquisitely sensitive instruments like the Planck satellite, we see a mottled tapestry of tiny temperature variations, mere millionths of a degree. These faint ripples are not random noise. They are the fossilized imprints of the universe's quantum origins. Those microscopic fluctuations born in the first instant, amplified by inflation into gravitational hills and valleys, are frozen into this ancient light. They are the seeds from which the entire cosmic web would eventually grow, the gravitational anchors for every galaxy, star, and planet. By mapping these subtle patterns with incredible precision, cosmologists can read the universe's vital signs. The precise statistics of these hot and cold spots tell us the universe's age, about 13.8 billion years. They confirm its geometry is flat to within a remarkable margin of error. And they provide a definitive inventory of its contents, revealing the exact proportions of dark matter, dark energy, and ordinary matter that we have detected in no other way. This fossil record is our direct window into the engine room's initial conditions, validating our theories of inflation and nucleosynthesis. Studying the cosmic microwave background is like discovering the original architectural plans for reality, a blueprint that hints at a profound and elegant symmetry written into the laws of physics themselves. Symmetry is the silent mathematics of perfection, a principle so fundamental it underpins the very laws of physics. It means that a system remains unchanged, identical to itself, even when you rotate it, mirror it, or move it through space and time. The universe, in its first moments of existence, was a state of near-perfect symmetry, a unified and featureless realm where all forces were one and particles were massless, buzzing around at the speed of light. But perfection is unstable. For our universe to become rich and complex, for matter to clump into stars and for life to eventually emerge, that perfect symmetry had to break. This breaking was not a flaw. It was the necessary creative act that gave the cosmos its character. Think of the early universe as a searing, formless magma. As this cosmic magma cooled, it crystallized, not into minerals, but into the distinct forces and particles that build our reality. The most dramatic example of this is the electroweak phase transition. In the universe's first trillionth of a second, there was one unified electroweak force. But as the cosmos expanded and cooled, this single force underwent a profound split, like a single road forking into two separate highways. It broke into the electromagnetic force, which gives us light and chemistry, and the weak nuclear force, which governs radioactive decay and powers the sun. This separation was made possible by a cosmic field that permeates all of space, the Higgs field. As the universe cooled, this field switched on, like a universal viscous medium. Particles that had been zipping around at light speed began to interact with this field, slowing down and acquiring the property we call mass. Some particles, like photons, slipped through untouched and remained massless. Others, like the W and Z bosons that carry the weak force, became very heavy. This is the Higgs mechanism, the process that gave substance to the universe. Without this crucial symmetry breaking, there would be no atoms, no chemistry, no structure. Everything would be an eternal, radiant, and featureless fog. The energy released during this phase transition was immense, fueling the next stages of cosmic evolution. This pattern of unity followed by creative breaking is the engine of diversity. The quest for a grand unified theory is an attempt to rewind this cosmic film, to find the original, perfect symmetry from which all forces, even gravity, once sprang. We are trying to find the single, elegant equation that existed before the universe cooled and crystallized into the complex reality we know. This pursuit of ultimate unity forces us to confront a final, inevitable question. If the cosmic engine had a beginning and has been running on its own power ever since, where is it all headed? What is the ultimate fate of this self-sustaining machine? The universe's own internal dynamics have set it on a course toward one of several possible ends. The leading forecast, known as the heat death, presents a profoundly quiet finale. As dark energy continues to push galaxies apart at an accelerating rate, the cosmos will expand forever into a state of maximum entropy. Star formation will cease as interstellar gas is depleted or becomes too diffuse to collapse. Existing stars will slowly burn out, one by one, their fires extinguished. Over trillions upon trillions of years, even the black holes will evaporate via Hawking radiation, their mass returning to the void as a faint, final whisper of energy. The universe will become a cold, dark, and incredibly dilute soup of fundamental particles, where the temperature approaches absolute zero, and no further work is possible. The cosmic engine, having run down completely, will settle into eternal silence. A more violent alternative is the Big Rip. This scenario depends on the specific nature of dark energy, if its repulsive force grows stronger over time. In this future, the acceleration would not just separate galaxy clusters. It would become overwhelming. First, it would tear apart galaxies, then solar systems. In the final, catastrophic moments, the force would rip apart stars and planets. In the last fraction of a second, it would tear the very atoms and atomic nuclei that constitute all matter into their fundamental, unconnected components. The fabric of spacetime itself could be shredded, ending the universe in a single, definitive rupture. The fate of everything hinges on the precise balance between the push of dark energy and the pull of matter and the geometry of space. Our current observations point strongly toward the endless expansion of a heat death, but the mystery of dark energy leaves the door open for other possibilities. What if the expansion were to slow and reverse? This leads to the speculative but compelling ideas of the Big Crunch or a Big Bounce. If the density of matter and energy were high enough to overcome dark energy's push, gravity would eventually halt the expansion. The universe would begin to contract, slowly at first, then with increasing speed. Galaxies would rush together, the cosmic background radiation would blue shift into a searing heat, and the entire cosmos would collapse back toward a singularity, a fiery implosion mirroring the Big Bang in reverse. This Big Crunch might not be the ultimate end, however. Some theories suggest this collapse could trigger a rebound, a new Big Bang that births a fresh universe from the ashes of the old. This is the concept of a cyclic universe, an eternal, breathing cosmos with no true beginning or end, only an endless cycle of expansion and contraction. This contemplation of cosmic fate brings a philosophical weight to our journey. It reminds us that the engine room's operation, for all its self-sustaining majesty, may have a final state. Yet the possibility of a cyclic cosmos offers a more eternal perspective, suggesting that the power to create and destroy may be an unending process, a fundamental rhythm written into the code of reality itself. This endless cycle of death and rebirth may be the universe's ultimate operating principle. We are accustomed to thinking of time as a straight arrow, flying from a definite beginning toward a distant end. But what if the cosmos is a phoenix, perpetually rising from its own ashes in an infinite loop of cosmic seasons? This is the radical vision of cyclic cosmology, a class of theories suggesting our universe is just one chapter in an eternal story. The brilliant physicist Roger Penrose offers one of the most compelling versions of this idea with his conformal cyclic cosmology. He proposes a deeply elegant, almost poetic mechanism. In the far, far future, after the last black hole has evaporated and all matter has decayed into its most basic particles, the universe will be an unimaginably vast, cold, and empty expanse. In this state of near-nothingness, a profound mathematical symmetry emerges. Because there are no massive particles left to define a scale, the infinite expansion of this old, dead universe can be mathematically rescaled, or conformally transformed, to look exactly like the hot, dense, infinitesimally small starting point of a new Big Bang. The end of one eon becomes, through this geometric alchemy, the beginning of the next. The universe forgets its scale and is reborn, its history erased but its potential renewed. This is not a collapse and bounce. It is a seamless transition where the ultimate future smoothly connects to a new beginning, creating an endless chain of eons, each with its own unique history but governed by the same timeless physical laws. Other cyclic models paint a different, yet equally astonishing, picture. Some theories, born from string theory, suggest our entire three-dimensional universe is a membrane or brain, floating in a higher dimensional reality. In this cosmic ocean, our brain could periodically collide with a neighboring one. Each collision would release an unimaginable firestorm of energy, which from our perspective inside the brain would look exactly like a Big Bang, igniting a new cycle of expansion and evolution. Another classic idea is the oscillating universe model, where the gravitational pull of all matter eventually overcomes dark energy, reversing the expansion. The universe would then contract in a big crunch, not to a true singularity, but to a state of immense density and heat that triggers a rebound, a new Big Bang. In all these visions, the cosmic engine room is not a one-time construction that will eventually run down. It is a perpetual entity, an eternal machine. Each cycle is powered by the transformation of the previous one. The dispersed energy and evaporated remnants of the old cosmos become the raw fuel for the new. This represents the ultimate form of self-powered existence, a universe with no need for an external starter and no final termination. It simply is, and always will be, a continuous process of becoming. This cyclical view fundamentally challenges our linear perception of time and existence. It suggests that creation and destruction are not singular events, but two phases of an endless, breathing cosmic rhythm. What does it mean for our place in the cosmos if our entire history, from the first star to the last thought, is destined to repeat in some form, across an endless expanse of time with no beginning and no end? Our ability to stand back and question the cosmic engine implies a deep connection between the observer and the machine. We are not just passive witnesses to a pre-programmed reality. We are a dynamic part of the system's own self-expression. This brings us to one of the most profound questions in all of science and philosophy. Why would a universe, so perfectly tuned to generate its own power and structure, also inevitably give rise to conscious minds capable of understanding it? The laws of physics did not need to allow for this. They could have produced a cosmos of silent, unconscious complexity, a beautiful but unobserved machine. Yet here we are. The anthropic principles offer a framework for grappling with this mystery. The weak anthropic principle is a simple statement of logical selection. It says that the universe we observe must be compatible with our existence as observers. We could not find ourselves in a universe where the constants of nature were incompatible with life, because in such a universe, there would be no one to do the finding. It is a cosmic version of the observation that a fish lives in water because it could not live anywhere else. The strong anthropic principle takes a much more daring step. It suggests that the universe must have properties that allow life to develop within it at some stage in its history. This moves from a statement of conditional observation to one of apparent necessity, hinting that the emergence of conscious life is a fundamental feature of the cosmos, not a random accident. Then there is the most speculative and mind-bending idea of all, the participatory anthropic principle. Pioneered by physicists like John Wheeler, it proposes that consciousness itself plays a crucial role in bringing the universe into concrete reality. In this view, the universe is a vast, potential-rich system, and the act of observation by a conscious entity is what collapses the countless possibilities into a single, definite reality. It is as if the cosmos built a magnificent engine room, but it required an observer to flip the switch from possible to actual. This is not to say we create stars by looking at them. Rather, the entire evolutionary chain from the Big Bang to the human brain might be a single, self-consistent loop where the universe develops the capacity to observe itself, thereby completing the circuit of its own existence. While these ideas push the boundaries of testable science, they force us to confront an astonishing possibility. Self-awareness may not be a quirky byproduct of a lifeless mechanism. It could be an integral, perhaps even inevitable, feature of a truly self-sustaining cosmos. The engine room does not just generate power and structure. It generates meaning through the emergence of minds that can perceive its beauty, unravel its laws, and wonder at its origins. We are not just living within this system. We are the universe becoming aware of itself, adding a profound layer of introspection to the cosmic machinery. This realization invites us to consider our own responsibility within this vast, self-powering entity. The universe has spent billions of years building a system so complex it can now look back at itself. We are that gaze. Every atom of carbon in our cells, every molecule of iron in our blood, was forged in the heart of a long-dead star and scattered across the cosmos by its explosive death. These raw materials, generated by the universe's own internal processes, have now coalesced into a form capable of asking how it all happened. Our scientific quest is not separate from the cosmic engine. It is the engine achieving a new level of self-regulation. We are a feedback loop of consciousness, a way for the cosmos to monitor its own performance, to understand its own rules, and to ponder its own origins. This transforms our role from passive inhabitants to active participants. Our drive to map the cosmic web, to decode the quantum laws, to peer back toward the Big Bang, is the universe engaging in a profound act of self-reflection. This perspective does not diminish our significance, it elevates it. We are not accidental tourists in a meaningless void. We are an emergent property of a self-sustaining system, a tiny but vital spark of awareness in the vast, dark engine room. With this awareness comes a profound responsibility. The same laws that gifted us consciousness also grant us the power to alter our local environment, to steward or squander the planetary resources that are our immediate home. Our existence is a testament to the universe's creative potential, and our future is now a part of its ongoing narrative. Our understanding is never complete, always evolving, pushing at the very boundaries of what is possible to know. Our cosmic questions are now being answered by a new generation of mechanical senses. Giant telescopes and delicate detectors are reaching across space and time, directly probing the universe's hidden machinery. The James Webb Space Telescope, floating 1 million miles from Earth, acts as a time machine. It collects the ancient, stretched light from the first stars and galaxies, allowing us to witness the epoch of reionization as it happened. We are watching the universe lift its own primordial fog, observing the very engines that cleared the cosmic stage for all future acts. Meanwhile, deep underground, in abandoned mines and beneath mountains, another hunt is underway. Extremely sensitive experiments, shielded from cosmic rays by tons of rock, wait in the profound silence and cold. They are designed to feel the faintest tremor, the minuscule kick of a hypothetical dark matter particle, known as a WIMP, bumping into an atomic nucleus. Catching just one such signal would be a monumental breakthrough, finally identifying the invisible matter that forms the skeleton of our reality. These experiments listen for the ghostly substance that holds galaxies together. On the surface, immense laser interferometers like LIGO and Virgo have given us a completely new sense. They do not look for light, but for the subtle stretching of spacetime itself. Their long, perpendicular arms detect the faint ripples from collisions of black holes and neutron stars that happened billions of years ago. We are no longer just watching the cosmos, we are feeling its vibrations, listening to the echoes of its most violent events. Each gravitational wave signal is a direct message from the warped geometry of gravity, confirming the dynamic nature of the engine room. Back on Earth, the largest machine ever built, the Large Hadron Collider, smashes protons together at nearly the speed of light. In the resulting fireballs, temperatures and densities not seen since the first microsecond of the Big Bang are recreated. Here, we are not just observing the universe, we are actively experimenting on it, teasing out the fundamental rules that govern matter and force. It was in this collider that the Higgs boson was discovered, providing stunning confirmation of the field that gives particles mass, a cornerstone of the cosmic process of symmetry breaking. These are not separate investigations, but a unified assault on the unknown. The data from a telescope informs the models for a collider, and the discovery of a particle refines the search in an underground lab. And the next wave of explorers is already on the horizon. The Euclid Space Telescope will create a colossal three-dimensional map of the universe, charting the distribution of billions of galaxies to measure the precise influence of dark energy across cosmic time. On the ground, the square-kilometer array, a forest of radio antennas spanning a continent, will trace the flow of cosmic hydrogen along the filaments of the dark web, watching the universe's infrastructure build itself in real time. Every photon captured, every vibration recorded, is another piece of the puzzle. We are no longer just speculating about the engine room, we are inside it, reading the gauges and listening to the hum of its generators, actively refining our blueprint of the self-powering universe with every new observation. This relentless pursuit of unity is the universe's final, unspoken command. For centuries, physics has been a story of separate kingdoms, with one set of laws for the very large and another for the very small. Yet the cosmos is one seamless entity, and the ultimate goal of science is to find the single, elegant framework that describes it all. This is the dream of a final theory, a so-called theory of everything. It would be the master blueprint for the cosmic engine room, a set of equations so profound they could explain not only how the universe operates, but why it has the precise properties it does. The challenge is monumental. General relativity paints a masterpiece of smooth, curving spacetime, a deterministic landscape where gravity is geometry. Quantum mechanics, in stark contrast, reveals a frantic, probabilistic world of chance and uncertainty. Unifying them is like trying to write a symphony using two completely different musical languages that refuse to harmonize. The implications of success, however, would be breathtaking. Such a theory would reveal the universe's deepest logic, showing how all forces and particles emerge from a single, fundamental principle. It would tell us what spacetime truly is at its most fundamental level, and whether concepts like the beginning of time have any meaning at all. This quest is not merely an academic exercise. It is a fundamental human drive to comprehend the totality of existence, to see the cosmic engine not as a collection of disparate parts, but as a single, integrated whole. Finding this final theory would represent a pinnacle of understanding, a moment where the universe's self-written code is finally deciphered. It would complete our journey into the engine room, revealing the ultimate source of the power that has lit the stars, woven the cosmic web, and given rise to minds capable of asking the question. This journey through the engine room of existence reveals a cosmos that is fundamentally self-sufficient. From the quantum foam to the cosmic web, we have traced a power source woven directly into the fabric of reality. It hums in the vacuum's restless energy, accelerates the void through dark energy, and forges stars through gravitational collapse. This is not a universe that was merely set in motion and left to wind down. It is a dynamic, self-regulating, and self-sustaining entity, an active participant in its own continuous creation. Recognizing that we are an emergent part of this incredible, self-powering system is a profound realization. It is humbling to know we are built from stardust, and empowering to understand we carry that legacy of cosmic ingenuity within us. Let this exploration be a starting point for your own curiosity. The universe's greatest mysteries are not locked away, but waiting for the next inquiring mind to uncover them. We would love to hear which idea from this journey resonated most with you. Share your thoughts in the comments below, and subscribe to continue exploring the wonders of existence together.